All right. Hello, everyone. So today we're going to continue our conversation on relational algebra. So this is where we stopped last time. We talked about cross product, and cross product is one of the key, probably one of the most important, if not the most important, relational operator or algebra. And the reason for that is the other, mostly whether it's select, rejection, they really focus on a single relation. But in order to write any kind of interesting queries, you want to be able to connect dots. You want to be able to join and connect the tables together. And the cross product has the basic foundation. At the face of it, it's not an efficient way of doing joins, or it's not an efficient way of combining records literally randomly from one table to another. But from the modeling and from the representation, it is powerful enough that can capture the basic intuition or the basic construct behind doing joins. So again, quickly go over it, and then we're going to look at some interesting example. So cross product given two relation S1 and S2, basically just look at a pairwise combination of all records. So for every record in S1, it gets paired up with every record in R1. And so the result is include n square, assuming the size of each relation was n. And so that becomes the basis for any kind of joins. And we talked about two variants of joins. One is the more generic type of join, which is the conditional join or theta joins, which joins to relation given certain operation or given certain condition. For example, we can join R and S as long as the SID ID of one relation is smaller than SID ID of the other relation. And the basis of it could be you just do a cross product, and based on the filtering condition, you can eliminate any unwanted tuple or any unwanted record. And they also looked at echo joins, and this is basically equality. So you want to do a cross product, but then filter out any rows, any combination for which the SID, the echo joint equality, does not hold. So again, you can think of it, you do the sort of the brute force cross product followed by filtering. Of course, none of these is an efficient way of doing joins, and this is not the way the database will do the join, but from conceptually, that's cross product in combination with the selection is powerful enough to model any kind of joint condition. And that's the key essence of cross product. Any question? So this is what we covered last time. I just wanted to kind of give just a reminder before we get into more interesting kind of queries. All right. So now the questions of division. And this is an interesting one, especially if the first time you're looking at it. And the question is very simple. The type of queries you want to be able to do is find sailors, for example, who have reserved all boats. And let's just look at example what that means. So this is our reserve relation, you may say, is that this is the sailor ID and this is the boat ID. And let's say this is our boat relation. And now if I say division A divided by B, give me all the sailor who have reserved all boats. Given the instances of the boat that we only have one boat. So what would be the answer? What is the answer of all sailor who reserved all boats in this case? So A divided by B1. Has S1 reserved P2? Yes. Has S2 reserve P2? Yes. Has S4 reserve P2? Yes. So the answer pretty simple is that if this is our boat relation, if this is our boat table, then finding all sailor who reserved all boats, and this is all the boats that we have, it gives us S1, S2, S3, and S4. So does the division problem make sense? Is that clear? Just a query. Now, how to find that answer, that's a different question, but just the definition of it. What does division means in this case? Okay, so another example, if the instances of our boat is P2 followed by P4, and we say divide A by B2, in other words, saying that we have only two boats, P2 and P4, and return all sailors who have reserved all boats. All sailors who have reserved both P2 and P4. So what would be the answer here?
S1, S4?
S1 and S4, yeah, because S2 has, well, actually S2 only has P2 and it doesn't have P4. And the fact that S1 has P3, it doesn't really change anything here because this is what we are dividing it by. And finally, if we say the set of our boat is P1, P2, P4, and then we do the same division, well, the only one that actually have resolved all these three will be S1, and none of the other ones would be qualified. So now this is the division operator. And now the question is, how do we do this with our 5 basic relational algebra operation, namely selection, projection, cross product, and the union and the intersection, the set base, ones. So any idea, how do we go about solving this problem? We looked at the problem of how to do joins. We said, well, we're simply going to do a cross product between the two tables, and then we're just going to disqualify any record, any paired record that do not satisfy the condition of the join or the equality condition of that particular attribute on which we are joining. So what would be the sort of an idea in order to get division composed of those basic relational algebra operator? Any thoughts? Again, you can just brainstorm it. I think we can spend the next 15-20 minutes kind of experiment with few ideas. So any thoughts? How do we give an A and how do we give an B1? How do we produce this relation? And this is 3 examples. Can I just follow the strategy we talked about with the join? Is that is sufficient? Would that work? If not, why it wouldn't work? What happens if I were to just do a cross product of these two relations and then try to remove the rows that don't fulfill what I need? What would be the issue? Why is that? Why can't I just follow the exact same strategy? if I were to join these two relations, what would I get? Let's say if I do a cross product, and let's say I want to do an equality join. So kind of join it whenever there is a match between P&O of A and a P&O of B1. What would I get? What would be the result of the join of this relation? Would this join the first record? No. Would P2 join the second record? Yes. So if I were to do the join, just a basic equality join, this would be a qualifying record. S2P2 would be another qualifying record. S4 and P2 would be yet another qualifying record. Well, actually this one as well too, S2 and P2. So I would get 4 qualifying record, S1, S2, S3, S4. I would actually get all 4 joined by P2. Then I can do some projection. I could potentially get this relation out. So if I were to simply do an equality join and do a projection on it, it will work for this particular instance. Does that make sense?
To clarify, are you saying the cross product between A and B is A slash B1? Sorry.
Division.
Right, division. Okay.
No, I'm not saying that's the way. I'm saying for this particular instance, and if you just kind of use the more higher level operator like join, like equality join that we just looked at an example, equality join is basically a cross product of the two relations and dropping any tuples or any records that do not satisfy the equality condition. And if I were to just do an equality join between these two tables, I would get S1P2, S2, S2P2, S3P2, and S4P2. And then if I were to just project out the SNO, I would actually get this table.
Okay.
Does that make sense?
Yeah, thank you.
So now, but it works for this particular instance, but the question is, does this solution actually work in all instances? Because you want to be able to find a solution that just not work for one particular case. It should be work for any given A and B, it should work. It shouldn't just be, well, we got lucky and perhaps just work this time, but it doesn't work in other cases. So now, would it work for B2? Would that same solution work for B2? Yes or no?
No.
So why wouldn't work for B2?
Because I think the result, if you were to apply the same result, it would be all the S1, S2, S3, wait, yeah, it would be S1, S2, S3, S4.
Yeah, so yes, basically since their P2 is in there, exactly all of these will qualify. This will again come into the results. So why is it that it didn't work? So what is the issue that we're seeing here? Doing that equality join, what query are we actually answering? Are we really answering that finding sailors or find all sailors who reserved all boats? Or that simple-minded solution, all it returns all sailors who have booked at least one boat? Because as long as one of these boats, they have at least reserved one of these boats, it will show up in our result, and and it won't, but it would just show up on the result. But it doesn't allow us to ensure that they have reserved all boats. This would only just give us the name of the sailor who have reserved one of these boats. And again, if we were to apply B3 and sort of do an equality join between B3 and A, we will actually just get the same result, S1, S2, S3, S4, because S1 have reserved at least one of these boats, S2 has reserved at least one of these boats, and S4 has reserved at least one of these boats. So definitely that would not work. So is that clear? Any question on that? So any thoughts? How do we now sort of strengthen or become a little bit more creative in combining A1 and B1, perhaps with a different way of using this cross product in order to ensure that not only at least one boat has been reserved, but also all of those boats have been reserved. Any thoughts?
Could you compare the results between P2 and P4? Just like, just whichever is the same, we would take it to A divide B2.
Yes, so that seems interesting. So let's see. So walk us through that that idea. Let's see how it works.
So with the result of the cross product between A and P2, we would get S1, S2, S3, and S4. And then if you do cross product between A and P4, you get S1 and S4. And now you have two different like results that you can, I think you can not join them, but I'm forgetting you can and them.
Okay, so let's kind of go back to, so first of all, which example are you doing? Are you doing A with B3? Let's kind of walk through it one more time. A, which one do you want to?
Oh, A with B2.
A1, B2, okay.
Yeah.
So we do A1 and B2, and then first we do a cross product between A and B2, is that correct?
Specifically A and the first, yeah, like P2.
How do you know? How can you pick P2? Because you don't know what's inside this relation. This relation could be these two relations could be any two arbitrary relations.
Good point.
So you can't hard code it.
Right.
But that's, I think you're on the right track. I mean, that's kind of, yeah, so you're thinking that's good. And we're just brainstorming. And you're kind of pointing out essentially the difficulty. Any other thoughts? So how about this? Let's kind of as an exploration. So let's kind of simplify our example. Let's just stick with A and B. And this is, in fact, the same A that we had in a previous slide. And this is B3 in the previous slide. And you want to find all sailors who have reserved all these 3 boats. What is this relational algebra is going to give me? Projecting out SNO from A. What does this give me? Gives me just a list of all sailors. Okay. So now I have the list of all sailors. I have the list of all boats. And I have the list of all reservations. Is that useful in any way? Can I utilize this in some way? And again, remember, the question I want to answer is that finding those sailors who have reserved all boats, namely all those boats that are listed in B. So now I can extract the list of all sailors. I have the list of all boats. What can I do with that?
Could you now do A with the cross product of this new list?
Do a cross product of, what's the other side of the cross product?
The new list that we just got.
So this cross product is?
Yeah.
Okay, and sure, and what would that give me?
Well, that would just give you the whole P1, the list that contains P1, P2. Huh.
You're getting close. You're getting close. Well, I mean, just if we kind of even do this in a brute force manner, we know we're going to use a cross product, and there are only 3 things. We've already picked 2 out of. We've already tried these 2. We tried these 2, don't seem to work. What's left? What else can we do? How many other cross product can be actually left here? We know these 2 don't work. We know this one, and this one doesn't seem to give us what we want. Any other cross product that we can do here?
I guess the cross product of B and A, the
Okay.
sign of A.
All right, and what would that give us? What would that give us? And that's the cross product of what you just said. Cross product of the list of all sailors and the list of all boats. If this was a reservation table, what this instance implies? What does it say about our sailors and our boats? If this was a reservation table, what can we say about our data?
Are we saying that all the sailor has access to all the boats, or?
Yeah, so if this was our instance, this says that every sailor have reserved every boat. Is that correct?
Yes.
Okay, how can we use now this information?
Sorry, could you repeat that again?
So what is this relation now tells us? If this was a reservation table, forget about that, we kind of constructed it. But if this was a reservation table, what we know about this table, what we know about this instance is that every sailor, this would represent a scenario, a possible world in which every sailor have reserved every boat.
Mm-hmm.
And this is our actual thing.
Yes.
This is the actual data, the reservation data. Anything interesting we can do with these two? This is the case where every sailor reserved every boat. This is the case that, well, this is the actual reservation. How's that? How could this be useful? And again, remember what we're trying to find. We're trying to find all sailors who have reserved all boats.
Yeah, so I guess we can do some type of relation between the one that we created and A to get S1, because S1 is the sailor that reserved all the boats.
Okay, so what would our next step be? Is everybody kind of seeing that our goal was to find all sailors who have reserved all boats. We just constructed the cross product that gives us a scenario in which every sailor have reserved every boat. And we also have the reservation data. So there seems to be, using these two, we should be able now to identify those sailors who have reserved all boats, because we know what it will look like if every sailor had reserved every boat.
Would we divide or something to get?
There's no division here. Here, all the operation that we have is cross product, projection, selection, and set difference. So we're trying to use just those basic operator to construct this.
We could get the complement of A from subtracting.
Yes, so getting this, subtracting it from A, is that what you mean?
Yeah.
Okay, and what are we going to get? What would this give us, this subtraction?
All the sailors who have, like, and all the boats who aren't reserved.
Say that again, all sailors who?
Didn't reserve the boats, or the boats that weren't reserved.
This is all sailors reserved all boats.
Right.
This is the actual reservation. So this is all possible reservation minus the actual reservation. What would be the output be here?
To get all boats that weren't reserved.
All boats that were not reserved. Exactly. So S2 and P4. So if you look at the original, so because one possibility was that S2 also reserved P4. But since the S2 didn't actually reserve P2, it will show up here. So what we're going to get here is the list of all boats that each sailor did not reserve. Does that make sense? So this was all possible reservation. This was the actual reservation. And this is the list of what wasn't reserved by each server, by each sailor. So what can we say, what would be our next step? We started with the actual reservation. We find all possible reservation. And then we found those sailor who at least there was a boat that they did not reserve.
Is it possible to delete from the sailor, or not delete, but subtract from the sailors from the original list and get only the inverse. So like you'll have all the sailor that does have all the boats.
Exactly. So for example, what we can do, let's just get the list of sailors. I mean, this is this relation and just with projection on it. Get the list of sailors that they haven't reserved at least one boat. So S2, S3, S4, which appears here, there are at least one boat that they didn't reserve. So this is the name of the list of sailor who at least didn't reserve one boat. Now the question that we want to answer is the list of sailor who reserve all boats. So what is that final step? This is the list of sailor who didn't reserve at least one boat. And we want the list of sailor who reserve all boats.
Subtract our second, but the third table, which is the sailor from this one.
So this is essentially becomes our disqualified tuples or our disqualified sailors. And as you said, now A minus our disqualified, A minus our disqualified tuple, it would give us the final set. So that means if I were to subtract this from this set, the only answer that would remain is S1. And S1 is the one who have reserved all boats. So with a series of composition of relational operators, we were able to construct the answer. And the trick was first construct all possible reservation, subtract it from the actual reservation, find those who didn't reserve everything, call them disqualified sailor, and go back to the original set of sailor and subtract disqualified sailor from, and that would give us all those sailors who have reserved every single boat. Any question? And this shows how powerful this idea of cross product, which is literally arbitrary pairing up every single tuple. You can not only you can construct joins, but you can construct really interesting kind of question by this very simple construct. Any question? Does that make sense? Okay. All right. So, and of course, this is the answer, only the S1. And this is, I'm going to kind of skip this slide. This is basically just expressing what we did in words. First, identify the disqualified tuples, and then deduct or subtract or remove the disqualified tuple from the original set. And that's just the basic idea of division. Instead of trying to solve it from the start, you first find it disqualified and then remove it from the original set. So now let's look at another question. So none of them going to be as interesting or I guess as challenging as the division, but let's look at other usage of these operations. So find the name of the sailors who have reserved boat 1 or 3. Any suggestion of how to answer that? Again, the relation of S1 is our sailor, and this is our reservation table. So find the name of all sailors who have reserved particular boat, which is boat with boat ID 103. So one basic thing we could do as a filtering condition on the reserve table, extract only the rows with row 103, meaning dropping any row that their boat ID is not 103. And the result of that, we join it with the sailor. And so that will give us all the sailor who have reserved boat 103, and then we just project out their name. So we can filter out row 103. So only extract this row and then join that with the, because we know this particular, I mean, if just looking at this row, we know that the sailor with the SID 58 is the only one who reserved boat 103. But since we want to find the name of the sailor, we need to join it to the sailor table and be joining the SID. So it's a natural join or the equijoin from SID to SID. And so to extract the name of this particular sailor, which is Rusty. Does that make sense? And another way of, you can kind of also construct a temporary relationship to sort of as a simple way of writing it down to kind of don't have this very long composition that is difficult to parse. So we can create a temporary relation. First, store the result of, so almost like think of it as a view. Of course, this is not a materialized view, it's just query rewriting. So put the, so first we have a selection on reserve, extract all those reservation that involves both 103, and then take that 103 reservation, join it with the sailor, and then put it into a relation temp2, and then take that relation temp2 and only project out the name. So to get the name of the sailors who reserve both 103. Another way of doing it is that I could just join first the relation reserve and sailor, and then filter out anyone that didn't actually didn't reserve both 1 and 3, and then project out their name. So now comparing solution 1, or solution 1 and 2 are identical. Solution 2 is just easier to read, especially as the query gets more complicated, but 1 or 2 are essentially identical. But is 1 and 3, what's the difference between 1 and 3? Definitely 1 and 3 are not the same. What's the difference? Is one more effective or more efficient than other, or they seem to be identical as well too? Which one would be more efficient and why? I mean, they're both doing the exact same thing. The only difference is that should I first filter out the reserve table and do the join, or should I first do the join and then do the filtering? Which one would be more efficient, you think?
I feel like filtering then joining would make it so there's inherently less to join, right? Which should be cheaper.
Exactly. So, and this is called push down predicate. So this is essentially your predicate, a condition. You push it down as much as you can. And the more push down predicate you do, then the input to the join, because the join is essentially the most expensive operation. And to reduce its cost, you reduce the input size. One way of doing it is to reduce the input size. Of course, you could have more elaborated join algorithm, but they're respectively smaller input size, faster join. So by pushing down the predicate, doing the filtering, and only joining on those tuples that you're absolutely sure that is actually going to end up in the final result, then of course it's going to be more efficient. So definitely solution 1 would be a lot more efficient, especially if you had thousands and thousands of votes. If you want to just filter out that one single one, and then you just joining a handful, as opposed to first look at all possible boats and then find out everybody who reserved any boat, and then at the last stage try to say, oh, I joined all of these. Well, I don't really care about them. I only care about the one who did 103. Now I do another filtering. So that would be a much, it would be too late. By then you've done so much work already. Okay, let's look at another example. So finding the names of the sailor who reserved a red boat, and assume there is a relation. There's a third relation that, given a bit ID, it gives us the color of the boat. So how do we go about solving this? So we definitely need an extra join, because we're assuming there's just an extra table that gives us the color. And essentially you can think of joining is you kind of adding on more information. You take the R1, you add S1 to it. Now you enrich the reservation data with the information about the sailor. Now you can imagine you extend this R1 again one more time by joining it to the boat relation to get all the attributes and the detail of the boat. And by just doing these joins, you're continuing to enrich the data. So we can first, as we discussed in the previous slide, is much better to just filter out as soon as possible. So we can filter out the red boat first, join it with the reserve. So now just looking at this join, it gives us the reservation for the red boat. And now the reservation for the red boat, joining it with the sailor, gives us the name for the reservation of the red boat. Make sense? Potentially a more efficient one would to, again, do projection sooner. So from the boat, not only we filter out the red, but you're only projecting out the bit ID. So we don't carry any other information for the boat. We only carry out the bit ID, because that's the only thing that it's needed to be joined to the reserve table. So for example, if the boat has 100 different attributes, we don't read those extra 100 attributes. And that's actually a lot more effective. If, for example, in L store, if you have column store, is really you can just focus, you can do those projection really efficiently, but basically you don't read anything. For the row store, of course, it's different. You're still reading the data, but at least if you imagine you read the data and then you have this tree of operators and you're pushing the data across up in this tree, starting from the leaf, the less data, the fewer rows and fewer columns you push up from one operator to another, from one memory location to another, well, it's going to speed up your query evaluation. And so it's also now, in addition to be beneficial to push down your predicate, if you can do projection early on, then it also saves transfer of the data from one operator to another. So only doing the projection, it's only taking out the bit ID of the boat. And once you did the reservation, join it with the reservation, the only thing that you really need is the SID, because you only need the SID to join it with the sailor, because you only need the name. So again, and you don't need to carry your boat ID after joining it with the reservation. So even the bit ID is no longer needed when you're joining it with the sailor. So that's another, dropping another column, less information being carried out from one operator to another. So this will give us a more efficient query plan than the first one. So slice and dice the data as early as possible, slicing as much fewer records as possible and fewer columns. Of course, if there is a column that you may later need, either the user needs it or you need it for perhaps a join later on, well, you can't drop it. But if it is possible to drop a column, then it's important to do it as soon as possible. And the optimizer, I mean, these are what the optimizer typically does, it creates a set of candidate plans and then look at a cost-based optimization, look at a cost-based plan to generate candidate plans, then determine a cost for each plan, and then it picks the most efficient one. Of course, the space is usually exponential, so you're not going to be able to solve it exactly, but it would be an approximate solution. Does that make sense? Okay, let's do another question. So find the sailors who have reserved a red or a green boat. So now in the previous one, we just did the red. How do we now kind of relax our condition to do red or green? How do we go about that? Is it significantly different from what we just did? Or is it just a minor extension?
Could we not just, when we make that initial filtering for the second relation table we don't see, just say red or green, or do we need to do one for each color separately?
Yeah, so
red or green.
Exactly. So because we're doing filtering and we can do any kind of predicate or any kind of condition, so we just relax that condition. Before we were just saying, just give us the red. No, it's okay. Let's just extract red or green. And then the rest is the same. Then we can just join everything and then extract out the name. Any optimization we talked about in the previous one equally applied here. And of course, we're pushing down this predicate. We're not going to first do all the joins and then later filter out if it's not red or green. We will do that early on. But what if, I guess maybe just quickly go to the, what if we say the or, can we replace that with the and? Would that also work? Well, what would that give us if we just make that or and and?
I mean, if we don't have multiple color fields in the relation, then it would give us nothing, right?
Exactly, because we're kind of saying the color is both red and the color is also green. So there's a contradiction. So if we were to just replace it, this both relation will just be empty. Or the result of this selection. I mean, the predicate is still valid, is a valid Boolean predicate, but it's always false. So there won't be any, the query will just produce no result. So now that's the next question. Find the sailors who have reserved a red boat and a green boat. So how do we go about doing that? Can we build on our last strategy in order to construct this more complicated case? Nothing is as exciting as the division, but still more. So again, we can just follow systematically what we did before, is that we could create a temporary red, find all the reservation for red, and find all the sailors who have reserved the red boat. So essentially finding the sailors who have reserved the red boat, find the sailors who have reserved the green boat, extract the green from the boat, join it with the reserve, get its SID out, So SID of the sailors who reserve the green boat, list of sailors who reserve the red boat. Now what? We do have the intersection operator, so finding the intersection of all the SID that appears in both the red and the green, and then joining it with a sailor to extract their name, to find all the sailors who have reserved both red and green. So again, this is really, I mean, these are really simple example, but it shows these simple operators, how powerful they are. And in practice, you may kind of see examples of having 15, 20 joins in your query, and it could be pages and pages long. A SQL query could be pages and pages long. And by these simple building blocks, you construct more and more interesting type of queries. Okay. So now find the names of sailors who reserved all boats. And we could just, for the simplicity, use the division, but we know we can always replace the division with the formula that we had early on. So reserve divided by boat, this gives us the name of the sailor who reserved all boats. And then we can, once we find their SID, then we can go ahead and get their names. And if you want a kind of specific type of boat, the sailors who reserve a particular type of boat, then in that relation, the initial boat one, we can constrain it. So say that, for example, they only reserve interlake type of boats. So that filtering, or they only find the sailors who reserve all red boats, or find the sailors who reserve all interlake boats. And you can sort of push down that predicate into that, the boat relation. Any questions? Okay, so that's our relational algebra. And so we looked at these basic 5 operations, and we can really build really powerful analytics just using these 5 operations. And again, it is a testament to the success of this field. These 5 basic operations have allowed building application, database application for nearly 50 years, actually more than 50 years now. And so that concludes our today's lecture. In the next lecture, which is, believe it or not, is going to be our final lecture, we're going to look at SQL. And so that will complete the language and the expressiveness of the course as well too. So if you have any questions, I will stay around. I'm more than happy to answer them. And if not, good luck on milestone 3 and have a wonderful day.